Okay, so this is Giant Planets from the Inside Out, chapter 26. So the idea is to start with the inside, the interiors of giant planets, and then move out to the atmosphere, then go from solar system planets to exoplanets and see what we can learn on planet formation. So I'd like to thank my colleagues, Leigh Fletcher, Ravit, Masahiro, Ikoma, who is here, Mike Leigh, and Vivien Parmentier for the work. But first, I'd like to take a little picture of all of us for good memory. Hopefully, the last conference with masks, hopefully. And I would like to thank the organizers also, who had a really tough job of organizing that through COVID, the change of editor, unruly SOC members. And so I'd like to give a round of applause for, especially in Sukasan. Thanks a lot. It's been really great. And it's great to cross communities on this wonderful subject. So, I want to use that too. So this is a comparison of Jupiter and the Earth to remind us that how big, how large a giant planet is. And I want to stress that, oh, is it working? Yeah. Okay. I want to stress that we now know Jupiter's mass as well as that of the Earth. We have 9 significant digits, a very, very high accuracy thanks to the Juno spacecraft. The Earth, of course, is 300 times less massive than Jupiter. Notice that it has a tiny atmosphere, only 1 millionth the mass of the planet itself, whereas Jupiter, of course, is a giant planet. So you could consider that everything is the atmosphere. There's no surface. And this is a reminder also that we live on a fragile planet. So this is the mass of CO2 that it contains. This is what the mass that humans added since the industrial age. So we have limited resources, and so it's a reminder that we should be careful. So given that, why studying giant planets? Well, I think it's really important to remain curious. It's really important to have conferences like this where we can meet. And giant planets are a wonderful topic because they play a major role in shaping planetary systems. They contain gas that's acquired during the early formation of planetary system and the solar system. And also, and maybe in this community it's less well appreciated, but they're great laboratories to study atmospheric dynamics because they're very different from the Earth in the sense that they have no surface, but also condensates are always heavier than the dry air, so tend to sink. It's the opposite on Earth. So what methods can we use? Well, we have the simple thing first to probe planetary interiors is to consider the density. Well, this is not working very well, so maybe I'll stay here. So with a mean density like that and models, you can relate the measurements from your theoretical results. If you have equation of state, opacities, an age, then you can retrieve a bulk mass of heavy elements, and we'll see results obtained with that approach, obviously. But then, especially in the solar system, we have the possibility to do gravimetry. So it means that when we have a spacecraft coming close to the planet, we have a measurement of the gravity field. We're measuring these gravitational potentials, the J's here. And we can also calculate that theoretically This is related to the interior density profile. You have here contribution functions that show that we are getting information on the planetary interior, mostly to the outside of the planet, but we're making our way from outside in. This was a situation before Juno was launched towards Jupiter. We had J4 and J6. It's already interesting, but some discrepant measurements. On the first pass of Juno, we were able to get a much, much better gravitational moments, J4, J6. After a few passes, sorry. Okay, I'll just use it for the laser. After a few passes, we got an extremely high accuracy measurement. We can't even see the error bar. So here, this is the situation for the solar system planets. We have a very high accuracy for Jupiter. We have an order of magnitude less, but still very high thanks to Cassini around Saturn. And of course, much less good quality data for Uranus, Neptune, because they were just visited by a flyby of Voyager 2. So we don't have good precision. We don't have J6, for example. Notice that we have a determination of K2, so the tidal interaction. So that's also something that can be used to constrain the interior. For exoplanets, obviously, it's much, much harder. There's a possibility to measure K2 in systems that are very peculiar, so-called fixed point eccentricity. We may know just one system like that, and it's not even completely sure it is in that configuration. And in that case, we can actually use that as a constraint to get relatively weak constraint on the core mass of that planet. But in the future, hopefully, we'll be able to get planetary shape with extreme precision photometry. And that would be extremely interesting. We'd get the H2, from the shape of the planet, and that's also linked to the interior structure. So we've had a real revolution since PP6 with seismology. Seismology was discovered in Saturn, finally, thanks to the Cassini mission and thanks to perturbations in the rings. The rings are a great amplifier of the normal modes of Saturn. As you can see that, we can see them evolving. It's a definite measurement of normal modes. It was shown that you have to invoke G modes and actually mixed F plus G modes in order to explain the observations. This is great work by Jim Fuller. And so it shows you here that in order to have G modes, you must have a stable region in the planet. So we have access to a new variable through that method. Okay, so on Jupiter, we have promising measurements. We've been trying from the ground. Of course, Jupiter doesn't have these great rings, so we cannot use the same method. So from the ground, we've been able to make progress. There's two teams in the US and then our team in Nice, the US and Japan, working on that. This is a Doppler image of Jupiter. Unfortunately, through COVID, it's been hard. And last year, we were hoping to be able to finally get continuous data. You know, Jupiter is moving up in the northern hemisphere, so it's getting more favorable. But then Japan was hit by a typhoon. This is the Okayama telescope that is being used, and unfortunately, the dome was damaged, so it's not usable. So if someone in the audience knows how to resolve things, I know it's probably quite expensive, but it's used also to monitor exoplanets, so it would be a very valuable use of resources to repair that telescope, and then we can have these continuous observations and hopefully detect these modes. We can, of course, probe the atmospheres as well through usual optical IR spectroscopy. Of course, we know that James Webb is coming in the field now and has started its revolution. I want to show a few images of Jupiter to remind us what a planet looks like and with all its complexity. This is from Mike Wang with Gemini at 5 micron, this wonderful image of Jupiter showing this hotspot, and it was imaged simultaneously with Juno in the optical at high resolution. You can see all the complexity of the atmosphere there. We also, of course, have near-infrared JWST images now, so that we will be able to study, to look for especially disequilibrium species, evolution with time, etc. But we also have radiometric sounding. And so the idea is to go to longer wavelength and then have the possibility to go through the clouds and really penetrate deeper than even the water cloud base. We have for that ground-based antennas with the VLA and ALMA. We're limited, unfortunately, from the ground due to synchrotron radiation. So Juno has a set of antennas that are able to do that from close up, and it's been highly successful in doing that. So those are different snapshots of brightness temperatures measured with these antennas, going from the top is at 0.7 bars to the bottom at more than 200 bars. And so we can see the evolution of the structures in the deep atmosphere. Then lastly, in 1995, we were able to probe a giant planet atmosphere in situ with the Galileo probe down to 22 bars. This is where the probe fell into one of these hotspots. So it measured very low abundance of water and really puzzling measurements. Unfortunately, we don't have a comparison, so we would really like to send another probe to other giant planets like Saturn and Uranus in order to have points of comparison. Okay, let us now plunge into the solar system planets. And I will just directly show you the results of interior models from this wonderful data for Jupiter, Saturn, Uranus, and Neptune. So there's been quite a bit of work on all these planets in the past 5 to 6 years. As you can see, we have Jupiter and Saturn, which are mostly made of hydrogen and helium, with deeper down some fraction of heavy elements. Uranus, Neptune, on the contrary, have only 1 to 4 Earth masses of hydrogen and helium. The rest is heavies. And the noticeable difference is that we're now envisioning that the cores of these planets should be diluted in the envelope and not well defined. I'll come back to that. So in terms of heavy elements, when we consider models with equations of state that we can that we're less confident with, that we're more confident with, we have total masses between 18 and 33 Earth masses or so, most of it being in the dilute core and a small compact core, if any. So Jupiter is enriched in heavy elements compared to the Sun by a factor 4 to 7, say, from interior models. In Saturn, we have more constraints thanks to seismology, but also it's maybe harder work. It's great work that has been done by Chris Mankiewicz and Jim Fuller, but only one set of modelers so far, so the range of possibilities is much narrower. But so it means 18 to 20 Earth masses in total of heavy elements. Again, they're pointing to a dilute core with most of the mass of heavies. And in Uranus-Neptune, we have less accuracy. Let's say they're mostly made of heavy elements. There's a big caution to be made that all this work assumes more or less adiabatic profiles, and it's possible that we could depart perhaps strongly from adiabaticity, and then this would yield higher values of Z. So for Jupiter, we have to realize, though, that it's really difficult to get models that fit all the constraints, because these constraints are so tight. And we have tension in the models that generally produce low abundance of heavy elements in the envelope that's incompatible with the spectroscopic constraints. So there's various recipes to go around that. One is to assume a negative heavy element gradient, so that Z is increasing, is decreasing inward as you go down in the atmosphere or in the molecular envelope. And this was first proposed by Florian Desbras and Gilles Chavrier. Another possibility is to invoke a higher internal entropy. So you'd need both higher temperatures in Jupiter and perhaps some super adiabaticity somewhere in the atmosphere. This is something that we've been working on with Shamila Miguel and Saburo Howard. We have a recent paper out. And then there's a possibility that there's a stronger than expected differential rotation, and that's been worked by Burkhard Millitzer, also published recently. So I want to point out that the uncertainties in the equation of state remain, in spite of really important and key progress. For Saturn, we have somewhat lower but similar tensions, so that the predicted heavy element enrichment in the molecular region of Saturn is lower compared to the spectroscopic constraints. So about the dilute cores, we have uncertainties. Well, for Saturn, the constraint is relatively tight in these models, so this dilute core should concern the inner 60 Earth masses. Saturn is 95 Earth masses in total. In Jupiter, it may extend all the way to the inner 150 Earth masses, but solutions with a dilute core extending only to the inner 60 Earth masses are also possible, but with higher entropies in the interior. For Uranus and Neptune, we want to stress that this cartoon is just represent one set of possibilities, but actually the interior could be well mixed with ices, rocks, and some gas mixed, and possibly a gradual transition. We don't have strong constraints, so we need really more measurements for these planets. A few words about the interior structure. Sorry, I skipped something. Okay, well. This is for Uranus-Neptune. This is a phase diagram for water. We're going through the superionic region where oxygen atoms are bound in a lattice. And it's been found that recently from new ab initio calculations that this should behave as a solid. so which would have strong consequences for the cooling of these planets. But this is true if you have water that's sufficiently pure, and we're not sure it's the case, and we don't know what would happen when you have a mixture of rocks, gas, and ices. We've made great progress on rotation. We've been able to measure the depth of the zonal flows in Jupiter and Saturn with just lower limits in Uranus-Neptune. This is great work from Yohai Kaspi since a decade ago, showing that you can use the thermal wind equation to link the winds that we observe to density perturbation and gravity anomalies that we observe. So that's definitely progress in that direction. One real surprise from Juno with this microwave radiometer is that the deep atmosphere is very complex. You can see here ammonia abundances that were retrieved. Ammonia is condensing here where it's black, so at around 0.5 bars. So we were expecting all these regions to be uniform. It's not the case. We have ammonia vapor that is still variable down to tens of bars. So it may be related to local storms and what we call mush balls, so mixture of water and ammonia that are brought down in the atmosphere. But the message here is that the picture is that giant planets are not simple, fully convective, homogeneously mixed objects. They're more complex than that. So coming back to Jupiter and Saturn, this is a phase diagram of hydrogen and helium, where we have also some questions here. So in the literature, we had since the last PP6 chapter, these ab initio simulations that were available showing that Jupiter and Saturn just reach this region where you have a helium rain, so that would explain what's happening here. But there's new experimental data that is puzzling with a very high critical temperature. So that would change completely the picture. Models have not included that so far, and we need other determination. This is done with high pressure experiments that are very costly. A few words about static stability. We have hints, or more than hints, that these planets are not fully convective. So already for Uranus-Neptune, this was used to explain the lack of heat flux of Uranus compared to Neptune. We now have a definite determination that there's a big stable region in Saturn somewhere to have these mixed FG modes. In Jupiter, the situation is not as clear, but we have some evidence that we need static stability in the deep atmosphere to account for observed anticyclones. We may need a stable region to break the winds. It seems the Lorentz force is not sufficient. We need maybe a stable region to account for the observed magnetic field. And also, we're getting, it's not a direct measurement, but an inferred dynamo core radius that's around this region. And so far, it should be related to some stability, but it's still to be determined what it means. Okay, with this slide, I want to remind you that those are very dynamic atmospheres. They're very variable, so you have to observe them for a long time in order to understand what's happening. We have strong seasonal variations in Saturn, for example. We had this gigantic storm in 2010. We have storms coming and going every 4 years or so in Saturn. and lots of very interesting phenomena. Please read the chapter. There's a whole section from Leigh Fletcher discussing that with some implication for exoplanets as well. So this means that we can have atmospheric abundances. This is a quite busy plot showing all that we know in terms of abundances, both for major species like CH4, NH3. We have H2S. It's an important new measurement in all these planets, but also disequilibrium species here. And you can see that they're stacking with an enrichment of around a factor of 3, 4 in Jupiter. Then it's more like 7, 9 in Saturn, and like 50 in Uranus, Neptune. So the bulk enrichments are higher, derived from interior models, because you have these all this mass in the inside of heavies. Okay, so let's move to exoplanets quickly. So since Hayashi Sensei is watching, I want to show a Hayashi track for planets. So this is an HR diagram, and this is how giant planets evolve. First, they contract and heat in the inside, then cool until you reach Jupiter today. But when they're heated, like hot Jupiters, they cannot remain on that track, and they have to develop a radiative region to get out of it. So with that, although there are complications because there's lots of processes that have been invoked to because these hot Jupiters are too wide, so we have to slow this contraction. So we have this radiative region that should develop, and we don't know how deep it should extend to. But the important point here is that based on hydro simulations, we believe that mixing through the radiative zone should be fast enough so that it should not be a barrier for heavy elements to be present in the atmosphere. So based on these kind of models and these measurements, we can infer bulk compositions for exoplanets. And this is work that, well, I did a long time ago, and then Daniel Thorngren and Jonathan Fortney did this wonderful work where they selected the planets for which we know what's happening best and derived this correlation or anti-correlation between bulk metallicity and planet mass that we can use. Okay. We have now spectra, so we can retrieve atmospheric abundances in brown dwarfs, directly imaged planets. See, it's more difficult for exoplanets in transmission, spectroscopy, or emission, but Webb is going to change the picture, as we've seen. Though we have to be careful that there's a lot of steps in order to go from observations to elemental abundances. But it's quite amazing to see the list of species that have been detected. So we have escaping hydrogen helium, ices, alkalis. So this is mostly with HST, JWST now. And then ground-based high resolution is becoming more and more powerful to detect other species, like rock-bearing species, like iron, magnesium, and things like that. So this is becoming highly interesting because all these elements are hidden from view in Jupiter, Saturn, Uranus, Neptune. In hot Jupiters, they appear because they're so hot. So here's a plot showing elemental enrichments as a function of mass. This has been done by Mike Line. This is the solar system line. This is if we take exoplanets and we use the Thorngren recipe, but we partition mass with a 10% in the atmosphere, 90% below. And then we add HST transit measurements, we have large error bars, so we have to be a bit careful with that. It seems that oxygen is subsolar generally. We still have to explain that. Direct imaging planets are here. And then we have high resolution spectroscopy. This is really nice work from Broggie and Line. So with directly imaged planets and then some hot Jupiters. So what we can infer is that between 50% and 99% of the heavy elements must be sequestered below the photosphere. So we can also look at CO ratios in hot Jupiters. It's still quite difficult, quite tricky to do that. So this is a plot for brown dwarfs and directly imaged planets compared to stars. You can see that brown dwarfs tend to have a slightly higher C2O ratio. Then for directly imaged planets, we seem to be lower and higher metallicity, but it's still early. The sample is quite small, so we have to make progress on that. So let me finish with a few words on constraining planet formation or giant planet formation. We envision 4 stages of planet growth. We have a first phase where we have a compact core that grows. This is the usual Pollack et al. Approach. Then we're forming something that is like a dilute core. So it means that you're simultaneously accreting gas and heavies. And then we have this fast envelope accretion phase that may be limited by gas supply. So at the end of those 3 phases, we have this situation, a compact core, then something that's more diluted, and then a homogeneous envelope on top. And what's envisioned is that atmospheric enrichment will occur either by late accretion, giant impacts, or upward mixing. So actually, upward mixing is something important where we've had progress with these kind of simulations showing that the envelope mixes relatively easily, and any gradient of composition should be eroded efficiently down probably to 20% of the planet mass as shown here. So it's difficult to imagine that a dilute core could be very extended. Okay. Okay, so now accounting for observed abundances, these large bulk Z values compared to atmospheric enrichments point to formation by core accretion, especially in the smaller mass planets. Jupiter's 3 times solar metallicity can be accounted for, but we lack more systematic studies. We would like to have studies for all the planets in the solar system, and including also accretion and mixing, which are important processes. So I want to point out that Jupiter has also a high noble gases abundance, that 2 to 3 times solar. So that's very puzzling, because those have to condense at very low temperatures, around 20K or so. So it had been proposed already in the last century that Jupiter may have formed at large orbital distances. But it's also possible that it accreted gas that was enriched by cold temperature dust that went to the inner solar system. We're going to come back to that. So isotopic constraints must be accounted for. For example, Uranus and Neptune's low D2H values implies that ices that accreted did not fully equilibrate with the envelope. We have this wonderful plot from Bernard Marty here showing deuterium and nitrogen isotope ratios, with Jupiter being really solar, and all the rest of the solar system being away from that. So what it means, it has a strong implication. It means that the NH3 that we see couldn't have been accreted by the material that are present in the solar system nowadays. So this material had to have disappeared. So there's two ways to do that. Again, form Jupiter at large orbital distances beyond the N2 snow line. And then by another possibility is by accreting gas that was enriched by originally cold temperature dust and including photoevaporation. So this is something that is important to keep in mind. Okay, so there's hints of isotopic ratios that are measurable in exoplanets, so stay tuned for what's happening. A word of caution, when linking abundances and isotopic ratios, please read the corresponding section in the chapter. Okay, I'm going to skip overdense giant planets. This is just the spectrum from JWST. We have really great measurements now. We're becoming able to tie these atmospheric abundances to bulk abundances, and there's a lot of work to come about that. So this is my summary slide. I want to stress that we've gone a long way on Jupiter and Saturn with Juno and Cassini, but still we need to understand convection in these hydrogen atmospheres and these abyssal atmospheres with no ground. For giant exoplanets, we have a lot that can be done, especially now with JWST. So the perspectives are great, and I want to stress that the decadal NASA decadal survey recommended a flagship orbiter and probe mission to Uranus, so we are building that, thinking about it with NASA, ESA, and any partner that is interested. It will be a fantastic mission. Look at this JWST image of Uranus, and I want to thank you all here and answer questions with that. Thank you.
Okay, so now the time for the discussion.
Yeah. Shigeru Ida and Exeter. Thank you, Tristan, for this impressive review. I mean, it's very exhaustive, number of topics you covered, and excellent review. Thank you very much. I have a question and a concern concerning the constraint arising from the diluted core and the formation models. And I'd like to know whether you will agree with me or not. As you pointed out, we basically all agree now that we must have a diluted core, call it the way you want, and somewhere in the outer envelope, a stably stratified region, probably due to double diffuse convection. So convection now, in terms of formation and evolution, is really a constraint. My point is that what I want to stress is that the constraint you've shown from the formation models, which suggest that everything will be diluted very quickly, are 1D model, and I would argue, and which do not take into account double diffusive convection. And I would argue that in 1D, of course, convection doesn't exist. You know, cross V doesn't exist in 1D. So my point is that if we want to have reliable quantitative constraint from the formation models, we must go to 3D. Do you agree with that?
Well, I would hope we can avoid it because it's simpler. But it's true that it's an issue, and we have to model convection with these compositional gradients in the right way. So yeah, going to 3D with hydro models would be definitely the way to go.
We're working on that. Thank you.
Yes, in the front.
Stan Metchev, the University of Western Ontario in Canada. On the topic of variable atmospheres and giant planets, you showed a slide, I think before your interior structure slide, that shows the variable wind speeds on Jupiter. I have a simple question, and probably it's a simple answer. What sets the differential in the wind speeds and the different latitudes, other than size and rotation? Or in other words, if I were to give you a brown dwarf with a known rotation period and presumably known size, can you tell me what the differential in the wind speed should be?
Oh, well, that's hard to do. What we can predict, generally, given a rotation period, is the number of bands that we should expect, because this is linked to the Rossby radius of deformation. But then we don't really understand what sets the wind speed in giant planets in our solar system. We know it's linked to solar heating and to rotation, and also their interior heating. But we don't know, for example, why we have more than 400 meters per second peak-to-peak velocity in Neptune and about 100 in Jupiter. So we don't have a recipe to say in a brown dwarf it should be that magnitude. In hot Jupiters, it's a little bit different because we have this day-night temperature difference, so that models can now predict the wind speed and with magnetic drag, a decrease in that wind speed for high effective temperature planets.
Thank you.
Back there.
Masahiro Kunitomo at Kurime University. So I'd like to ask differential rotation, so proposed by Militz et al. 2022. So if there is a strong differential rotation, then some instabilities would set in, like circulation or shear instability or magnetic Taylor instability. So the differential rotation should be flattened, but is it possible to sustain such a differential rotation until now?
Yeah, obviously, I mean, the particular solution Burkhardt proposed is viable with latitude. It should be, I mean, it should be indeed tested that this solution works and also fit the gravity data. But in terms of direct shear instability, I think we're not at that level. So it should be okay.
Okay, thank you.
Andrea Zella, Rice University. So my question is related to magnetic fields. So you briefly mentioned they can provide some constraint on Jupiter. I would like if you can expand on that a little bit. And related to that, there is hope that we might start putting some constraint on magnetic field of giant exoplanet using low frequency radio observation. Would that help constraining your structure model? We're talking about convection, for example. So, I mean, would that be important?
Well, thanks for the question. I for the sake of time, I was already a bit long. I didn't include the magnetic field maps, but you can find them in the chapter, and it's actually quite striking to see how different there are between Jupiter, Saturn, Uranus, Neptune, with Saturn having a purely axisymmetric field. Well, it's difficult to really go through that, but basically, well, it's not advancing well anyway. Basically, we have in Jupiter a field that is asymmetric between the northern hemisphere and the southern hemisphere. So it seems this require a stable region so that the two hemispheres are not completely interconnected. So it's through high resolution observations that we can say that. So for exoplanets, I'm afraid it's going to be difficult to have an interpretation and a constraint for interior models yet. But at least, I mean, if we have tendencies, if we have statistics, and then we can understand if close-in planets have a stronger or weaker magnetic field than planets further out of the same mass, then maybe we can surely gain some information about them. Yes.
Thank you.
The front.
JJ Zanesi, UC Berkeley. So it's really cool to see how effluents can constrain the interior structure of Saturn. I was wondering what the prospects were to observe F modes in giant planets undergoing high eccentricity migration, which are forming at short orbital periods?
That's an excellent question. And I don't know. The answer is really I don't know. But indeed, these planets are very interesting. And yeah, it should be tested, because this would be a way, if it works, it would be a way to get some valuable information.
Yes. Back there.
Shinsuke Takasawa, Osaka University. I have a question about the source of heat in the outer atmosphere of Jupiter and the possible connection with the atmospheric heating in the solar atmosphere. If we look at the solar atmosphere, we do see the spatially and temporally intermittent heating by magnetic field. And my question is that do you need the magnetic heating in the Jupiter atmosphere?
Oh, no, because Jupiter is neutral in the upper. I mean, in the atmosphere that we see, it's very much neutral. So magnetic field is not playing a role. But it's true that deeper down, and this may be related to this region where you have differential rotation. I mean, this region here. Where you have differential rotation and the medium is becoming conducting, then magnetic heating is certainly playing some role, and it's yet to be determined. Models do not include that.
Thank you.
Yeah.
Hi, Johanna Tusky from Carnegie EPL. Excellent talk, thank you. My question is, when we're looking at trends in giant exoplanet compositions, enhancements over their host star, and trying to draw conclusions about their formation, so something like the mass metallicity plot that you showed, how important do you think it is to compare those enhancements to solar versus the composition of that specific host star, if that makes sense?
Yes.
Is it important? Does it matter?
At that point, you can see here, I don't know why I'm not able to advance the slides.
I know the plot, the Thorngren and Fortney one.
It's, maybe here. Ah, yeah, okay. Oh, sorry. Here it's compared to the metallicity of the star. There's a lot of scatter. So at the moment, we're not at a point where it makes a difference, I would say. But hopefully with better determinations, also of the stellar metallicities, we'll get to a point where it does matter. And I'm looking forward to, to being at that point.
Okay, thank you.
Okay. D'accord.
Hello, James DeFrancesco, National Research Council of Canada. Yeah, that was a cool talk. Thank you so much for sharing that today. My question is regarding the intriguing anomalous abundances of the noble gases that you mentioned in Jupiter. And I just wanted to find out if, considering that these abundances, as you say, come from cold environments, if it's a viable explanation that perhaps there is delivery of such elements from, say, comets over the age of the solar system, or is that simply not high enough flux to account for such anomalous abundances?
Sorry, I didn't understand the last part. Could you repeat?
Yeah, I just wanted to know if comet delivery of perhaps noble gases over the age of the solar system could account for such anomalies.
No. It's first we've seen with 67P that the argon abundance in that comet is very low. And then, so you would need to bring a lot of comets, and then you'd be bringing also material that have the wrong D2H. So it's you have to do it through another way. So to me, Jupiter acquired these heavy elements through material that since have disappeared. So it's either either you form directly the planet very far, and then you acquire everything that condenses locally and then migrate the planet, or you migrate the dust because you're at very cold temperature, and you bring all these elements to the inner solar system, and you can accrete it as gas, but it has to be enriched. So you have to get rid of hydrogen and helium preferentially, but through these quains, through photoevaporation, those would work.
Okay, thank you very much.
Okay, maybe almost time. So the final question. So the
All right. I'm Kenji Kurosaki from Kobe University. I have a question for the. I'm very interested in the deep interior of the planet, but the deep interior is very difficult to constrain, I know. So my question is, how about some kind of how to constrain the deep interior by observation or theory? I mean, maybe equation states or tidal Q value or gravitational moment of the atmosphere. So how do you think about that?
Yeah, thanks. It's an excellent question. I think having gravitational moments, or K2, through a measurement of the shape of some of these planets would be really great. But it's going to be very difficult because we need a high accuracy on these measurements in order to make these constraints.
Yes.
So for the moment, that's the only possibility I see, except if we can measure, I mean, through these high eccentricity planets, some modes propagating. Otherwise, it's very difficult to get to the cores of these planets. But then we have other indirect methods. So hot Jupiters, we're seeing elements that condense at very high temperature, so should be hidden. And also we have things like white dwarfs or events where planets are destroyed, and they may bring us some information as well.
Okay, thank you very much.
Thank you.
yeah, we need to move on to the next talk. So please thank Tristan again.